is the important example of posterior and very basic example, but it has many, many implications. So I introduce these basic examples. Why I given theta comes from the normal distribution with mean theta and the variance 1. And theta follows normal distribution with the mean mu 0 and the variance sigma 0 squares. Then posterior can be obtained like this. Is the it is by the basic calculation. Here, mu 0 and the sigma 0 squares are hyperparameters, usually the constant values. The important property is that prior and the posterior are Gaussian, also Gaussian. The distribution of theta and the posterior of theta are the Gaussian distribution. And the right rule comes from Gaussian distributions. So this shows all Gaussian. So the posterior is the normal distribution. If prior and the posterior are the distribution of the same class, denoted by F gamma, then the posterior updating from prior is the updating gamma by using observed data. Here, in this example, the prior mean mu 0 is updated this value. And the variance of the variance in prior is updated to this value. So only the parameters are updated. And second, Bayesian estimator. Bayesian estimator means the posterior mean. The mean of the posterior distribution is a linear combination of MLE of theta and the prior mean mu 0. We can write the posterior mean like this. Here WN1, WN2 are like this. So the posterior mean called as Bayesian estimator is a shrinkage estimator to the direction of posterior mean mu 0. This shrinking property can make a bias because the MLE is unbiased aesthetically. But this shrinkage estimator can drastically decrease the variance, especially when the data size is small. So the bias and variance, the Bayesian estimator can make some bias, but the variance of Bayesian estimator can be very, very small. And WN1 is the wave for this estimator, and the WN2 is the wave for this. And WN1 is dominating WN2 as n goes to infinite. If you have many data, W1, N1 becomes 1. Here becomes 0. So we have many data, the W1 becomes larger and WN2 becomes 0. This can be interpreted as likely to dominate the prior, and the data dominate the prior. The prior effects diminish as the data size increase. So this shrinkage property of Bayesian estimator can be found in the small data size. And the third is that the posterior variance of theta is like this, and this goes to 0 as n goes to infinity. It has a very important implication in theoretical aspect because the distribution of posterior converges to certain Dirac measure. And if the Dirac measure degenerating at A is the converged Dirac measure, then you want that A equal to theta 0. Theta 0 is the data generating parameter. So if A is equal to theta 0, then you claim the posterior consistency hold. The posterior work well. It means that the posterior consistency hold and the posterior can work well. Here is the example of posterior consistency. First, it is the first posterior, and it is the second posterior, it's the third posterior, it's the fourth posterior, and it is the fifth posterior. Can you see the variance of posteriors? The variance of posteriors decrease. And as data size increase, the posterior goes from 1 to 5. Then we have many data. The posterior can degenerating at this point. It means the posterior consistency. Now I introduce the marginal product of Y. In obtaining posterior likelihood function and prior assumption, but there's no role of marginal product of Y in the posterior, but it is very important quantity in other aspects. I said 3 components and 3 approaches in statistical analysis. Usually in statistical analysis, we consider 3 components and 3 approaches. The 3 components is the data and matter, likelihood, and parameter. It is given, data are given, and matter, we specify the matter, and then we want to know this parameter. And the 3 approaches is inference, prediction, and model selection. Inference is about knowing theta, estimation of theta, point estimation, such as the posterior mean, maximum likelihood estimator, and interval estimation for confidence or credibility. It is the example of 1 minus alpha% credible interval. It is interval constructed by Y. In 1 minus alpha% credible interval means that the posterior of theta is included in this interval with a probability of 1 minus alpha. Usually we use the value of alpha as 0.05, usually 90% credible interval or 95% credible interval. The prediction is the for new Y star, then use the Py star given Y. Usually mean and the prediction interval can be used. induced from this quantity. And the second problem is the model selection. In Bayesian analysis, it is the problem of selection of priors. It is model selection and the selection of priors are equal. This is an example for model specification. If we use the prior PM, such that PM's theta m is equal to 1, where theta m is the parameter space having orders like this. If we can use these priors, then the posterior has the same properties. So all inference of Bayesians will be done on this parameter space. So the prior can specify the model. It's because the support of the posterior cannot be larger than that of the prior. If the prior mass is equal to 0, the posterior mass should be 0. Then, we are interested in the problem of model selection. What prior, what model can be better? The better model, the better prior we want. To assess this, the model selection problem arises, and if you have data Y and consider two models for simplicity, then the posterior of M1 for the model 1, given data Y is written like this. And to obtain this, you should integrate out like this. And what is it? The marginal probability with the prior P theta 1 given M1. So the marginal probability can be different. The marginal probabilities can be different with different priors. The marginal probability can be used to a model selection procedure through this formulation, and the marginal probability of Y is essential to obtain the posterior of models. But if the model probability of M1 given Y goes to 1 when Y comes from MI, model I, then the model selection consistency hold. It is the usual terminology in Bayesian theories. And note that the predictive distribution of Y star given Y depends on the posterior, like this, and the posterior depends on what? Prior. So if we use inefficiency or long priors, then all fails. Predictive distribution cannot work well, and the marginal probability of Y cannot be high. So the Bayesian model selection procedure is based on what prior can result in the high marginal probability of Y. It's the problem of selection. Here, I introduce some important property of posterior. This property is very, very important, and it can be used to many, many algorithms. It's the conjugate prior and the sequential posterior updating. Conjugate prior for likelihood, it means that if the prior has the functional form P theta give tau 0, then the posterior has the same functional form. It is a conjugate prior. Here is some examples, the normal model. It means that likelihood comes from normal and the prior is normal. And it means that likelihood comes from normal and the prior comes from inverse gamma. And likelihood comes from Poisson distribution and prior comes from gamma distribution. It's the formulation for normal model and the normal inverse gamma model and the Poisson gamma model. Here, we P prior on theta, and here we P prior on not theta 1 divided by the sigma squares. And here we P prior on theta. Then, by observing these three quantities, these three formulations, in this likelihood, theta has the argument quadratic term, linear term in the exponent. And the prior, theta has the quadratic term and the linear term in the exponent. The functional forms are the same. So the conjugate case. Here, we can show that the functional forms are the same with respect to 1 divided by the sigma squares. These are the same functional form, and these are the same functional form. And the rest Poisson gamma model, these are the same functional form, and these are the same functional form. So the generalization of conjugate prior in exponential family, it is constructed by the statisticians and others. The exponential family means the distribution having the following property exponential like this. And the prior, we use the prior like this. Then the posterior can be updated like this. Prior and the posterior has the same functional form. So if we use the exponential family for the prior and likelihood comes from exponential family, then the posterior is one of the exponential family. So the updating of parameters can provide the posteriors. And the more interesting property of the posterior updating is the sequential updating is possible. If we consider posterior theta given y1 and y2, by rewriting this posterior, we can show that it is proportional to this term. It is the likelihood function based on y2 only. And it is, what is this? It is the posterior given y1. So we want the posterior given y1 and y2, and it is obtained by the likelihood of y2 only by using the posterior given y1 instead of prior itself. So the sequential updating of posterior can be done by like this. It means that we observe data, the first data, we can construct the posterior, and from this posterior, we can construct second posterior based on the first and second data. Sequential updating can be done. And it can be used in Bayesian online learning very effectively. And this posterior can be interpreted as the accumulation of data. This posterior accumulated the information extracted from y1 to yk minus 1. Here is an example, the normal model, and BP prior on theta, simulated data from normal with mean 3 and variance 2. And in this simulation, posterior are updated sequentially. At the first, only one data. And the second, using two data. And each step, posterior mean and 95% credible intervals are drawn. Here is the path. The red line is the posterior mean. At this, the posterior of given 20 data. And at this, the posterior given 100 data. So the sequential updating can be possible, and the posterior mean vary with increasing data size, and the credible intervals become shorter. From this figure, we can know that posterior mean starts from a small value, almost near 0. Maybe it's the effect of prior, but becomes 3. Because the simulated data are from the normal distribution with the mean 3. And the variance decreases as data size increase is the variance. So the credible intervals become shorter. We only use 10 data, but if you use many data, this posterior mean converges to 3, and the credible interval, the length of credible intervals nearly become 0. This sequential updating has important implications. The posterior summarized information of observed data very, very well. And we observe the posterior. You should check about the well performance of the posterior. First, you should check posterior cannot be the same with increasing data size when Bayesian learning performance well. The posterior should vary with the increasing data size. In deep neural net and the other Bayesian learning, the posterior does not vary with increasing data size. There is a very severe problems. And generally, the variance of posterior should decrease with increasing data size. In some cases, many data are used. When many data are used, the variance of posterior does not decrease. It means the Bayesian learning does not work. It's the usual procedure for Bayesian analysis. We first model specification. It means that one model model selection, and choosing prior and checking the posterior reasonable. There's no problem. And obtaining the posterior and the Bayesian estimator, posterior beam mode and the credible interval and others. And last step is doing model selection procedure to find the better models. If we perform the model 1 and we performed model 2, and we performed model 3. The models, the performance of models can be compared, and the posterior of models can be calculated. Here is some comment about Bayesian sampling for the Bayesian. Note that the posterior is a distribution. It's not scalar. It's the distribution. So the sampling procedure, such as rejection sampling or MCMC, is required. Because in Bayesian, we obtain the posterior, and the posterior is the distribution, not scalar value. Thus, there are many sampling algorithms and sampling schemes for the posterior. And in this tutorial, we did not cover the sampling method, but there are many sampling methods, and there are many issues. In this section, I introduce property of posterior and the Bayesian non-parametric. About the Bayesian non-parametric, I introduce some definitions and important properties only. So in this section, theoretical aspect of posterior in parametric models and the Bayesian non-parametrics are introduced. We can know that the prior Frey's closure rule and the posterior predictive distribution and the marginal distribution of Y depend on prior. So the specifying prior is very difficult. We have some assumptions for the theoretical argument. First, theta has the dimension of P, and second is that we assume the observed data Y follows the law of Py given theta 0. We call the theta 0 as the data generating values. Here, the posterior is P theta given Y. It has the argument of theta, but it has dependence on Y also. In the previous slide, posterior mean is like this, and it depends on Y data. So the posterior P theta given Y can be considered as a random function depending on Y. It has the functional form with respect to theta, and it depends on Y. And we consider Y as the random, then this posterior is a random probability density function. So the all theoretical argument start from this randomness. It's the theorem of Gaussian and Ramada. They are very massive regulatory condition, but the result is that it means that the posterior distribution converges to this property, this distribution. This distribution is normal distribution. So the posterior converges to the normal distribution as data size increase. This theorem is called as Bernstein-von-Mises theorem, and which implies the three factors. The first is the posterior of theta converges to theta head and theta zero, because theta head converges to theta zero. And the posterior mean converges to the maximum likelihood estimator, and the posterior distribution converges to normal distribution. So usually, we draw the histogram of posterior. We can observe that symmetric and very, very similar to the histogram of the normal distribution. It is because of this theorem. And the second is that improper prior, the representative improper prior P theta is proportional to constant value. If you consider this prior, it is proper prior because the integrated out P theta is equal to 1. Then the posterior can be like this. But in this, these two terms can be cancelled. So this posterior can be interpreted as the limit of this posterior. So we use the improper prior like this. It can be interpreted as the limitation of this posterior. So the improper prior can be used in many matters. It has no problems in mathematics, but in parametric model. If non-parametric models are considered, it has severe problems. In practice, improper prior and pseudo-likelihood exactly likelihood, but very similar. Means the pseudo-likelihood can be used when the posterior is proper and has the consistence property. So the important part is that the posterior is proper and the posterior has the consistency property. If these two hold, there's no problem use of the pseudo-likelihood and the improper prior. I introduced some concept of hierarchical model in the lecture of Bayesian. These hierarchical models are very, very emphasized, and is the advantage of the Bayesian analysis. Left, Py given theta and tau with the model, and the theta and the tau are parameter and hyperparameter. Theta is parameter and the tau is hyperparameter, and theta depends on tau. Then we can the model like this. Is the data generating structure, and it is the prior for theta given tau, and it is the prior for tau. So we have two hierarchy for the prior. And the posterior can be obtained by like this. It's very simple, and it is not difficult to obtain. But if you consider the marginal prior of theta, you should integrate out with respect to tau, then the marginal prior of theta can be like this. It's like this. For this hierarchical approach, we can construct various marginal prior of theta. Example, if we consider this hierarchy, the variance is 1 divided by tau, and the tau, VP priors on tau as gamma. And VP prior 1 divided by tau exponential. Then the marginal distribution of theta, T distribution or Laplace distribution. So if we want the more various prior on theta, then we use this hierarchical approach. Many people think that this is too complex, so I use this T distribution or Laplace distribution directly. It can be a sound thing, but this hierarchy approach is better in some matters, and it gives more informative in many cases. So the Bayesian models usually use the hierarchical model, very, very complex hierarchical model.